Hello class, this is my suggested solutions for the practice exam we did from the independent, the Heffernan group 2013 exam 1. Okay, let's have a look. Question 1. Find all the solutions to the equation z to the power of 4 plus 2z squared minus 3 equals 0, where z is an element of the complex number set. Now, first thing we recognize is it's a trinomial and it's in the structure of a quadratic. So we can let u is equal to z squared to give us this quadratic in terms of u. Then we can factorize, equate it to 0 and use the null factor law to get solutions for u. Easy. And then we relate it back to z. So since u is equal to z squared, we get z squared is negative 3 and z, so that gives us z is plus or minus square root 3i. And z squared is equal to 1, so z is equal to plus or minus 1. Okay? And when you're stating all, you'll find all solutions. And when you're stating all the solutions, it's good to just put them again together as a list after a therefore statement, just like that. Okay. Next question. Plot the roots found in part A in an R-gain diagram below. So when we're plotting on the R-gain diagram, you're always going to start from the origin, start from 0. And there's the first one when z is minus 1. And z is positive 1. And here's another one, z is root 3. Now, where I positioned root 3 is about there. Now that's an approximation. First off, what the examiner wants you to know is approximately what is a decimal value of root 3. Root 3 to one decimal place is 1.7. So that's a little bit more than halfway. 1.5 is about there, 1.7 is about there. Okay, so that's an important thing to remember. 1.7 for root 3. Same with z equals negative root 3i. Coming down here to a little bit more than halfway. Okay, next question. Question 2. Find an antiderivative of x on square root of 2x plus 1. Now, we're going to do this by substitution, integrate by substitution. So we let u is equal to 2x plus 1. And then we have to work out the derivative, okay, our du dx to get 2. And we can rearrange that so that we have a half du, and that's equivalent to dx. Then we set up our integral. So the integral of the x function in terms of u becomes this. So we've got the square root of u down the bottom, and our dx is replaced with a half du. There it is. Now, we can't integrate just yet because we've got a little problem. We've got an x. Okay? Now, you can't have an x in there and integrate with respect to u because there's a relationship between x and u. Okay, you can't treat x as a constant either. X is not a constant, x is a variable. So the integrand has to be completely in terms of u before we proceed. So how do we do that? First off, we're going to draw on our relationship between u and x. Can we transpose this relationship for x? Yes, we can, and we will get this. So x in terms of u gives you this expression. You take 1 divide 2. So let's substitute that in. And so the half here multiplies with the half there, and we get a quarter. We'll have u take 1 over square root of u. Now, what's another way we could write this integral? 1 over square root of u is u to the power of negative a half. And that's going to be a factor multiplying our numerator, our brackets. let's expand the brackets. There it is, and now we've got a power expression, power term expression. So we know how to integrate power terms. We add 1 to the exponent and then divide by 1 plus the exponent for each term. There we go. And plus c at the end, of course, because it's a indefinite integral. Now, let's look at the question again. It says find an derivative. An antiderivative, implies just one example of an antiderivative. When it's plus c, that's a general rule to cover all possible antiderivatives. So to obtain just one or an antiderivative, we have to go ahead and simplify this. But before, what I forgot to do, we've got to get it all back in terms of x. U is equal to 2x plus 1. We've got to substitute that back in. Getting ahead of myself. And there we go, that's better. So there's our derivative, our antiderivative in terms of x. Okay, substituting the u value in. And I no longer have c. Okay, expand it out. Okay, when I expand it out like that and write it back with the square roots like I have in the question, that's the best form to give your antiderivative. And I'm going to make c equal 0 to have one unique antiderivative. Alright, for when c is equal to 0. There we have it. Next question. So a solution to the differential equation, here it is mx squared log of 2x. Okay, now x is greater than 0 and m is just a real constant. We have to find the values of m. So the first thing to do is, if that's a solution to the dE, then that is equivalent to y. Y is equal to that. Okay, and so what would be dy dx? And what would be the second derivative? So let's work them out. Y dash, or dy dx, is given by that. To obtain that, I had to use the product rule. So we've got a product of x squared with log of 2x. So using your product rule, I can differentiate it to get this expression. And then second derivative. So work out both y dash dash. There we have it. And let's now substitute them into our differential equation. There's dy dx minus x times the second derivative plus 6 times y. Okay, and we only need to do that into the left hand side for now. Let's simplify that. Okay, so just by expanding our brackets, the x times this bracket and the 6 times this bracket, expand it out, and then simplifying by their like terms so I can cancel them, we're going to end up with just this as a simplified left hand side. Okay, that is equivalent to the right hand side of the differential equation. And by expressing this left hand side in a form that's similar to the right hand side, by factorizing this negative 2mx outside of set of brackets like I have here, I've got the x term and a unit and a coefficient outside of set of brackets, I can relate them carefully. So I can see that this bracket 1 minus 3x log of 2x is the same as on the right hand side, 1 minus 3x log of 2x. So that implies the first part, the negative 2mx, has to be the same as negative 10x. And therefore m has to be 5. by dividing by negative 2x on both sides. So, what do you think? Let's have a look at the next question. So a box of mass 20 kilos is ascending, going up, accelerating at 4.9 meters per second up the rough slope. Rough slope meaning we've got some friction at an incline of 60 degrees to the horizontal. It is being subjected to a pulling force of 294 newtons directed up the slope, going up. Alright, so part A, show all the forces acting on the box on the diagram. Label each force. So what forces do we have? We've got pulling force, we've got a weight force, we've got a normal reaction force, and there's our friction force going in the opposite direction of motion. Okay, now it's important here to make sure your friction force is mu times n. Okay, because the object is in acceleration. It's moving. So it's got the sliding friction. Okay. Part B, show that the coefficient of friction, mu, is 2 minus root 3. Alright, so let's first resolve the forces into the horizontal direction, the direction of motion. So you've got this one, 294 newtons, so we can have that positive. And then we've got in the opposite direction, so subtracting a negative, mu times n. There. And then we have a component of the weight force. That's also directed down, so subtraction. Okay, and that component is the opposite side of this triangle, so sine of 60 degrees times the weight. And that is equivalent to mass times acceleration, so 20 kilograms for mass, and acceleration of g on 2. Why is g on 2 the acceleration? Well, the acceleration is 4.9. That is exactly half of 9.8, which is g. So it's convenient to write 4.9 as g on 2 for our algebra. Now, we have to work out what n is. Where do we get n from? N is determined from the vertical components, okay, perpendicular to the motion. So n going up and subtracting the cos component, the perpendicular component of the weight force. There it is, weight force times cos of 60. And so n has to be, for cos of 60 is a half times 20 gives you 10g, so that's 98 newtons. Let's substitute that into our first rule here. There it is. Sine of 60 is root 3 on 2. So the on 2 part divides into the 20 to give 10g times root 3. And simplifying that. And then to work out mu, we divide by 10g. And we get that expression, carrying out this little subtraction here, and we're going to get 196 over 98, and then the 98 here cancels out with that 98 to leave you just root 3, and 98 goes into 196 exactly twice, so 2 minus root 3 is your answer. There you go, we've proved it. Okay, and then the next question, the pulling force is reduced so that the box is now just on the point of moving up the plane. Do you remember what that means? On the point of moving up the plane, it's at equilibrium. That's the limiting condition, and the friction force takes the sliding friction formula, mu times n. What is the magnitude of the reduced pulling force? So here we have just at the point of moving. It's not moving yet, so acceleration is 0. So we have the pulling force P minus our friction force, which remember it's on the verge, so that is mu times n. minus 20g sine of 60 equals 0, acceleration of 0. So evaluate sine of 60, root 3 on 2, and it gives you 10 root 3g, and f is mu of n. Now from the previous question, we had worked out n to be 10g. That's from part A of the question. And mu, from also the previous question, is 2 minus root 3. So we've got to use that information again in this part. Substitute them in. There we go. And let's simplify by expanding and transpose 4p. Okay, which gives you 20g, which is 196 newtons. There you go. Next question. Question 5. Okay, so first, find the area enclosed by the graph of y equals sine squared x cos x. Now, for this domain of x, it's going from 0 to pi on 2. You have to recognize that is your first quadrant. And we have to find where this graph, the area is enclosed with the x-axis. Okay, so that's the area underneath the curve. We can't sketch it, so we don't know what the curve looks like. But we have to draw on some assumptions about sine and cos for angles in the first quadrant. So for the first quadrant, sine squared is greater than 0. That's positive. Okay, the squared of anything is always positive anyway, so that's okay. What about cos? In the first quadrant, okay, cos is also positive, so it's greater than 0. So if both cos and sine are positive, therefore y has to all be positive for all x values. Okay, so there is no crossing at all for the x-axis across this domain. That's good. I like that. Makes it easier to set up the integral. So the area now is the integral from 0 up to the minimum up to the maximum, because the function is all positive during that time. So the area will be some positive amount. No signed area. So we integrate this over those limits. We don't have a rule for this, so we're going to have to use trig identities and some substitution. First off, let u is equal to sine of x, and then du dx gives you cos of x. Derivative of sine is cos. Rearrange that. Now, before we do though, by introducing variable u for a definite integral with limits 0 and pi on 2, 0 and pi on 2 are x values. What would be, if we introduce a u variable, what would be the corresponding limits for u? So we got to work them out. When x is 0, for that bottom limit there, what is the u value? So u is sine of 0 is equal to 0. So that's good. What about when x is pi on 2? U is sine of pi on 2, and that is equal to 1. Okay, so we have to use these new limits for our new integral in terms of u. And there it is. Since du is equal to cos x dx, I can replace this part here, cos x dx. All that there is replaced with du. Okay? Now we can integrate with respect to u. And we get u to the power 3 on 3. And evaluate that from 0 to 1. Gives you a third squared units. Okay? Now, because we're evaluating across our new limits, we don't need to do anything about resubstituting u is equal to sine x back in. okay, because we have our u numbers. These are our limits in terms of u, and we can evaluate straight away. So there's the area. What do you think? Next question. Question 6. Okay. So let's go ahead and evaluate this cool looking integral. It looks a bit complicated, but I'm sure there's a way. First off, separate it into two parts. You've got your first term in your numerator, gives you the first fraction, and your minus 3 gives the numerator of the same denominator to get a second fraction. And we're going to integrate each separately. What happens with the first integral? Well, x over x squared plus 4. X squared plus 4. That's a quadratic, but we can't really reduce it to something. So we're going to do it with the substitution. X squared plus 4 for u, so du dx gives you 2x. Well, that's alright, because we've got the factor of x there in the numerator next to the dx. Alright, and by rearranging the du dx equals 2x, I can get a half du is equal to x times dx. Now that's really useful, because that can take this x with this dx, and those two are going to be replaced with a half du. Now all that is going to be put into the first integral only. We're not going to do anything with the second integral just yet. Now, like we did in the previous question, we've introduced a u variable into a definite integral with limits 2 and 2 root 3. So we got to get the u values for these limits. So for the lower limit, x equals 2, the u is the x squared plus 4. So 2 squared plus 4 is going to give you 8. What about the other x value, 2 root 3? So in x 2 root 3, the u value is 16. Okay, so we've got to rewrite our first integral now with these new limits for u and perform the substitution as well. So the half here from the half du, that's going to come out as a factor of a half out the front. And we're going to write with the new limits 8 and 16. And it's 1 over u after the substitution. And we're going to integrate that with respect to u. So there's our first integral simplified using the substitution method. Now, with the second integral, what we have straight away is we've got this factor of a 3 that doesn't seem to fit with the integral. We're going to take that 3 and bring out the front. Okay, and there it is there. But if I compare this to the formula on my formula sheet, I'm going to recognize that, hang on, this is pretty close to the inverse tan integral. And the inverse tan integral has a number on top over x squared plus a squared. Now the a squared here is 4, so the a number must be a 2. So if I'm going to put a 2 in the numerator, I have to balance it out and put a 2 down here in the denominator and bring that out the front. So there it is. There's 2 in the numerator, 2 down here in the denominator. They cancel out to give 1 really, but we're going to keep them there. And we've got that factor of 3 which was in the original numerator, and that's just come out the front. Does everybody understand that? So now we've set up our integral in the right form. Let's integrate both. There it is. So the first one is the integral of 1 over u, which is log. Remember to keep the modulus. Then we evaluate it from 8 to 16. We can write it in the top there. And then the second integral gives you the inverse tan of x on 2. Okay? With those limits, 2 and 2 root 3. Now, let's evaluate. Log of 16 minus log of 8. And then for inverse tan, we'll get inverse tan of root 3 minus inverse tan of 1. And then we evaluate each separately. What we have though here is log of base e of something subtract log base e of something else. So the subtraction of two logs, well, that can be simplified as the division of the arguments, 16 and 8. So 16 divided by 8 is going to give you 2. So that simplifies nicely. And then we evaluate inverse tan of root 3, that's pi on 3, and inverse tan of 1, that's pi on 4. You're just going to have to know them and learn them, because we can't look them up on notes, because we're not allowed to have notes for exam 1, and we have no CAS. So we must learn them, and we must be able to just recall. It's memory recall, ladies and gentlemen. So we get pi on 3, take pi on 4. And we simplify nicely. Our half here is going to come up and be a power of the 2, so 2 to the power of half is the same as just square root 2. And pi on 3 take pi on 4 is pi on 12, and we've got our 3 halves take pi times pi on 12 to give a pi on 8. And there's our answer. Alright, so a little bit challenging, but not impossible. And just take some practice. Next question. Almost there. Alright, so we've got a position vector of a particle at time t. And it's given by this vector function. Okay, let's find the acceleration of the particle at time t. So the acceleration is r dot dot. Now, to get that first, we have to work out what r dot is, the velocity vector function. And we do that through the process of differentiation. So let's differentiate our position vector to get the velocity vector, r dot. So you're doing the derivative of square root, gives us a to the power of negative a half, with the half of the square root coming out the front. Differentiate here now, 2 minus t squared to give us just negative 2t. And we still keep the vectors I and j, keep them separate. Now let's differentiate again to get r dot dot. Okay, and again we do 1 minus the power, and we bring the power and multiply out the front. So a half times negative a half gives you that negative a quarter there. And of course differentiating negative 2t to just get negative 2. Alright, so therefore the acceleration vector is given by this, and I've rewritten it just neatly to the power of negative 3 halves gives you a square root with an expression 2 plus t to the power of 3 inside the square root. That's how you would write it. Now we have to show that, part B, show that the dy dx is equal to negative 16 when t is equal to 2. So this is dy dx. This is like the derivative of a Cartesian equation. However, we've got a position vector with a parameter t. This is in parametric form. So how do we get dy dx from an equation involving parameter t? We've got to differentiate using the chain rule. So dy dx is dy dt times dt dx. Now this dt dx is just the reciprocal of dx dt, the derivative of the first part here. Now we can take those derivatives straight from the work we did in part A. dy dt, this derivative, is this part here, the derivative of the y expression. Now that's in the j component, so there's your j, 2 minus t squared, that is y of t. If we differentiate that, dy dt, we get negative 2t, so that's that one. And then dt dx, the next bit, well, that's just the reciprocal of dx dt. Dx dt is what we've got here, a half times 2 plus t to the power of negative a half. So if we do the reciprocal of that, we're changing the negative a half into a positive a half. Okay, or 1 over the negative, the bracket to the power of negative a half. And when we multiply, we obtain this. Okay, that's the expression in terms of t for dy dx. Now, we want to know that what is the derivative when t is equal to 2. So substitute t is equal to 2 into our rule, and we evaluate it, and we're going to get that negative 16. And we've proven it. We've shown that dy dx is equal to negative 16. There it is. Okay, how'd you go? Next question. Okay, so find the angle between the vector r of t at t is equal to 1 and this vector, negative I minus j. So, angles between two vectors. We've got one vector, r of t, and we can simply work that out when t is equal to 1. And we've got another vector. How do we find the angle between two vectors? Okay. First off, let's work out what r is at t equals 1. So evaluate r of 1. Substitute that into the position vector in place of t and simplify. And we get that, root 3i plus j. Okay. So the next bit is, first off, we recognize, hang on, that is in the first quadrant. It's a first quadrant vector. Okay, if we sketch that in Cartesian plane, we're going to recognize that is coming out into the first quadrant. And then, if I take that as a dot product, okay, with I, that's the horizontal. That's in the x direction. Essentially what I'm looking at is, here's a little Cartesian plane. This one's on the fly now. So it's a first quadrant vector. It's a vector coming out here. And you've got an angle that this vector, in angle theta, makes with the I vector, unit vector in the x direction. Okay, so I can determine that angle there by doing a dot product with the vector, with I, and then by relating using the definition dot product of two vectors is equal to the magnitude of each times cos of theta. Now, theta is going to be the inverse cos of root 3 on 2. And I have obtained that by performing my dot product, root 3 times 1 plus 1 from the j times 0, because there's no j over here. So, and the magnitude, the modulus of root 3i plus j, that goes to 2. It's the square root of 4 to give 2. And we divide over here to the left, and we've got, take the inverse cos to get the angle by itself. You can check it yourself if you like. And the inverse cos of root 3 on 2 is pi on 6. So our small little angle there, theta, that's pi on 6. Okay. Let's do the same thing for the other vector, this negative I, negative j. This is a third quadrant vector. That one's coming down here. Coming down this way. And that makes another small angle theta with the x-axis, negative I direction. So the dot product with I, and we have here the dot product of the two vectors equal to the magnitude of each, the magnitude of I haven't written down because I is just unit vector and the magnitude of I is 1. So you imagine there's a 1 right there between this modulus and cos of theta. That's not going to change much. And so theta, once we evaluate that, we're going to get the inverse cos of negative 1 on root 2, which is negative 3 pi on 4. So from I direction, from here all the way around, it's negative 3 pi on 4. Alright, so I'm drawing it again. Why am I drawing it again? There it is. So there's all the angles that I'm adding up. So I can see I can get the total angle between the two vectors by adding pi on 6 with 3 pi on 4 to give 11 pi on 12. There's our total angle between our vectors. So there you go. What do you think of that one using our dot product rule? Need a little bit of intuition to interpret our diagram and thinking about where those vectors are, but that's what some of the challenges of our exam. Question 8. Alright, so a region enclosed by a curve, y, the x-axis and the lines with equation x equals 1, x equals 3 is rotated about the x-axis. So find the volume of a solid revolution. Fantastic. These are good classic solid revolution problems. Do you remember the rule to find the volume of a solid revolution? There it is. Okay, pi times y, the integral of y squared. Now, we have to integrate between the lines x equals 1 and x equals 3. Alright, so y squared is, we're squaring this fraction here. And square the 4 to the 2 to get a 4. And we square the square root to just get x squared plus 4x. Okay, then we notice we've got in the denominator here x squared plus 4x. If I take out a factor of x, I've got two linear factors, and I'm going to separate these into partial fractions. So there it is. We've got an a on x plus b on x plus 4 partial fractions. So we've got to work out what the partial fractions is first. So get a common denominator and expand out the numerator there. And it gives you these two equations, a plus b is equal to 0 and 4a is equal to 4. So you get your results, a is equal to 1 and b is equal to negative 1. And it's a very good idea to practice this skill, partial fractions, and learn how to be able to do this quite quickly. It's about building efficiency and speed with this little problem there. Okay, that comes with practice. So, homework. Let's do our integral now of our partial fractions, where the original fraction is going to be represented by these two fractions here. So, our volume rule becomes this. Each is a log. Okay, so 1 on x goes log of x minus log of x plus 4. And because we're subtracting logs, we can write with the argument as a division. Okay, so it's good to recognize that and be able to do that straight away. Then let's evaluate. Evaluate it at 3 and then at 1. Do the subtraction. And we'll have our 2 3/7 and 1/3 there. And again, subtracting logs, it's a division. So we'll have the 3 times the 5 to give 15 on 7. Okay, and there's our volume. It's very important to put units cubed at the end. Okay, how'd you go? Oh, almost there. We're on for 40 minutes. Question 9. So the gradient of the tangent to the curve inverse sine x on 2 minus x squared y minus 5 at the point where x equals 1 is given by this expression. Okay, so that's the general form of the answer. The gradient of the tangent, and a, b, and c are real constants. We have to find the values of a, b, and c. So it's about working out the gradient of the tangent to this curve at x equals 1 and making sure our answer looks like this and stating what a, b, and c are. Let's try it. Have a look at the equation. This is not an explicit equation in terms of y to get dy dx, so we're going to differentiate using implicit differentiation. Remember how to do this one? You've got to differentiate the left-hand side expression with respect to x, and we also have to balance that by differentiating the right-hand side of the relation as well. Now, we're going to do that to each term. So first we differentiate inverse sine of x on 2, and then we differentiate x squared times y. Okay, now got to remember what we do here carefully. We get this. Now that there is your derivative of inverse sine, and you can look that up in your formula sheet at the back of the exam. Now here, that derivative is found by doing the product rule of this. So that is, derivative of x squared gives you 2x times y. Then the next bit is the x squared times the derivative of y with respect to x, and we call that just y dash for short. In problems like this, it's good to use the dash notation because you get to write less and you can make more sense of it too. So we transpose. We transpose to get this y dash. We want that y dash there by itself, but we're going to keep that x squared next to it because, frankly, when x is 1, we substitute 1 there and we just get y dash by itself anyway. This makes it a little easier. So at x equals 1, we're going to get y dash is given by this, but we've still got that y there. So what do we do with this y term? Well, how can we get a solution for y? Y can be worked out from the relationship at the top. If we transpose this for y, or x squared times y, as we did here, then substitute in x equals 1, we get this expression for y. Y is the inverse sine of a half minus 5, which is pi on 6 minus 5, at the value for y. So let's substitute that back into our expression for y dash. And there we have it. And then we simplify that down and we get this. Now, it's about, can we write this in the form that matches the structure of the answer that we're supposed to determine? Okay? And we can see by matching it, we've got A is the same as a 3, and the B is the same as 10, and the C there is the same as 3. So we state that at the very end. Everybody understand? Alright, last question, and it's only like 45 minutes, so we're doing well. We've done an hour an exam in 3/4 of an hour. Okay, oh, we love these ones. This is solving a differential equation. Particle has an acceleration a meters per second given by this expression in terms of v. Okay, now v is the velocity of the particle when its displacement from the origin is x meters. So given that v is equal to -4 when x is 1, find an expression for x in terms of v. So that is x as the subject in terms of v with as the pronumeral. So first off, a, acceleration, you recognize that as v times dv dx. That's the first bit. And then relate that to the right-hand side. Let's separate the variables, put all the v's, the v parts and dv all together on the left, and bring the dx on the right. Then we integrate. And an efficient way of integrating that's going to make use of the initial conditions as well, and this little method helps you to skip introducing your integration constant plus c. That's what is to set up with limits on your integrals, okay, and evaluate definite integrals. So your initial conditions, when v is equal to -4 and when x equals to 1, they're going to be on your lower limit. So the lower limit for v is your v value in your initial condition, and the lower limit for x is your x value in the initial condition. And then your upper limits are just your pronumerals v and x, because we want v's and x's in our rules. Okay. So let's start integrating. What we notice here is this structure matches an inverse sine rule. Okay, so does it? No. Let's see what we have to do. Right, we got to do it as a substitution method. So we need to have, looking at your denominator, we have a 25 take v squared. Now, if that is u, let u is equal to that, and I differentiate, then I'm going to have the derivative of the denominator up in the top here. So to make sure I've got a derivative, I've introduced the 2 on the v, and I balance it out by bringing a half out the front. And let's see the implications of that. So u is equal to 25 minus v squared. Differentiate that. du dv is equal to negative 2v. That's the derivative of our u expression. And then we rearrange this to get du. So du is equal to negative 2v. Okay, and there it is. I've got my negative 2v up in the numerator, and that together with dx, dv, that gives me the whole bit there, that bit, and that bit is going to be replaced with just du. Everyone understands the substitution method. It's a very important skill that you need to practice for both math methods and specialist maths. So there's our new integral, and that is something we can integrate straight away because it's a power term. And also on the right, when we integrate and evaluate on the right, the integral of 1 gives you x, and then we evaluate that at the limits of x and 1. X minus 1 gives us this on the right hand side. Integrate the left, and we're going to evaluate it at the limits, v, and for a v of minus 4. Because it was v is minus 4, and I've kept my v value, even though I've introduced my u, I have to make sure that I have v back in the integral. So I've redone my substitution. u is equal to 25 minus v squared. I've substituted for u back in with the expression 25 minus v squared, and now I can keep my original v value for the limits, and I don't have to work out corresponding u values for limits. So I evaluate my integral at minus 4 up to v, and I get this. And I can just transpose 4x. And we've done it, we've done the rule. Nice and quick. I don't have to worry about a plus c and then substituting in initial conditions and then working out c and so on. Straight away, it's very direct. Okay, so I've got the expression for x in terms of v. Alright, last part. Hence find an expression for v in terms of x and find the domain of this relationship. So to get an expression for v in terms of x, I have to transpose. I've transposed for v. Let's do that. So first we subtract 4 to both sides. Now, before I do anything else, we got this far, and I think, can I use this information to help me get a little bit about the domain? Yes, we can, and this is a very important little thing we got to consider. This little strategy also appears when you're finding, sketches of hyperbola from a loci equation. Okay, so what we're going to do is first recognize what was the domain on v. So since v ranged from the information in the question, ranged from -5 to 5, what is the corresponding range on this right hand side, this function of v? Okay, so we will have, when v is -5 or when v is +5, if we put that in there and evaluate, what value would we get? -5 squared gives you 25. 25 minus 25, well, that's a 0. There is 0. In fact, 0 is the most maximum number of this expression. What value of v would give you a minimum? Well, when v is 0, we get a minimum occurring. Okay, so if I put a 0 there, then I'll have 25 minus 0, okay, which we give the square root of 25 to give 5, and then times by negative. So -5 is your minimum. And there's your range, -5 up to 0. So if the right-hand side has a range of -5 to 0, then because it's equivalent to the left-hand side, that means x minus 4 also has that range of -5 to 0. Okay? So, some important things to think about there. Now, we can get a domain for x by adding 4 to both sides. So if I add 4 to the -5 here, I'm going to get -1. If I add 4 also to 0, I'm going to get 4. Okay, so x ranges from -1 to 4. Now, coming back to our transposing the formula. Okay, because we haven't done that yet. We just got the domain. So to transpose the formula from this line, I'm going to square both sides. Okay, and that removes the negative square root, and I get an x minus 4 squared. Then I'm going to subtract 25 and divide by -1, and I get this expression there for v squared. And finally, I can square root, and I've transposed for v. Plus or minus, I cannot forget, very, very important. Plus or minus the square root of 25 minus the x minus 4. And we did it. That's pretty cool. What do you reckon? Wow. I think that's it. I hope you enjoyed that. I did. Oh, last thing is we got to state the rule with the right domain there. And there it is. From -1, inclusive of -1, up to 4. Awesome. And we have finished. Well done, everybody. I hope that was helpful. If you have any further questions, please ask. And keep studying.